All right, so moving on to section 4.3, we're going to talk about determinants and how they can be used to calculate area and volume. So in your book, it's just called determinants and volume, but we're really going to narrow in on area and then just assume that it works for volume. And you'll see what I mean, especially with the first theorem. So we're starting the section with the theorem. And it says if A, so if a matrix A is a 2 by 2 matrix, the area of a parallelogram determined by the columns of A is the determinant of A. Oh, sorry, is the absolute value of the determinant of A. Okay, so do you guys remember the parallelogram law that we learned very early on when we were learning about vectors? But it basically says if A is a 2 by 2 matrix, then we can actually use that matrix to determine a parallelogram, and we can use the determinant of that matrix to figure out the area of it. And so it's always going to be the absolute value because area is always a positive number. Also, I'm going to put this in parentheses. If A is a 3 by 3 matrix, the volume of a parallelepiped determined by the columns of A is the determinant, the absolute value of the determinant of A. All right, so a parallelepiped is kind of like a parallelogram, but in 3 dimensions. So we're going to be using volume for that. And we can actually use a matrix to determine what the parallelepiped looks like. And to find the volume of that parallelepiped, we just take the absolute value of the determinant of A. So let's look at a specific example. We want to find the area of the parallelogram whose vertices are 0, -2, 5, -2, -3, 1, 2, 1. All right, so this is our parallelogram, and I'm actually going to graph it. So let's take some time to graph these points in our parallelogram. All right, what do we have here? 0, -2. I'm going to use a different color. All right, connect our dots. Pretend that this is correct. All right, so this is our parallelogram. And so This parallelogram is kind of difficult to figure out the area because we have these vectors in like random places. So what we want to do is to translate the parallelogram so that one of these vertices lands on the origin, and that will really help us out. All right, so the first thing that we're going to do is to translate the parallelogram to one having the origin as a vertex. All right, and so you can choose any one of these to center our parallelogram. I'm going to choose this one and change this vertex to be at the origin. So to do that, I'm going to subtract 0, negative 2 from every single one. So we are going to subtract 0, negative 2. And so that is going to give us 0, 0, the origin, 5, 0, negative 3, 3, and 2, 3. I'm just subtracting 0, negative 2, so 0 from each one of the x values, and then negative 2 from each one of the y values. And so then we're going to get another parallelogram. All right, let's go ahead and draw this one. All right, so I got 0, 0, 5, 0, negative 3, 3, and then 2, 3. If you're still drawing, please pause the video. All right, so this new parallelogram that we've drawn, it's the same. It's just been shifted, right? So this is the same as the original. It's going to have the exact same area, which is what we're looking for. Okay. All right, so the next thing we need to do is figure out the matrix that determines our parallelogram. All right, so how do we do this? Well, let's take a look. Remember, our parallelogram is completely determined by whatever this vector is and whatever this vector is. We can find the rest of what it looks like. So I'm going to call this vector B1. So that's this one. All right, so what vector is this? This is the vector 5, 0. All right, and then it's also determined by this vector. I'm going to call it B2. All right, this is the vector negative 3, 3. All right, so our parallelogram is going to be determined by the matrix 5, 0, negative 3, 3. And based on our theorem, if we take the determinant of this matrix and take the absolute value, we get 15. And 15 is the area of our parallelogram. All right, so we're going to check out one more theorem in the next video.